Continuing with section 1.3, we now look at another example. So this says the logistic equation for population P in thousands means if there are 2,000 people, then the value we will take for P is 2. If there are 5,000 people, the value is 5, and so on. So the logistic equation for population P at time t is given by dP by dt equal to P times 2 minus P. This is called a logistic equation. It has some, actually we will not study it much later on, but P is the population. So previously we have seen the population growth, simple population growth, like dP by dt equals K times P. So this is similar to the decay model. This is called the growth model, but not for a human population, but maybe for a bacteria population or some like growth rate. Before that we saw when we had a negative here, so that is called the decay rate, and this one with the positive K is called a growth rate. We can easily solve that by separation of variables. We can do this also by separation of variables, but we are not going to go into that detail, although you can do it by converting the left hand side. Once you move the P quantities to the left, which both of these will go, P and 2 minus P, so then you can do it by partial fractions method. But here we are just going to look at its direction field and answer some questions. So it says the direction field is given below. So this is the direction field. Now these are just 1, 2, 3, 4 are kind of the values of the t variable and the p. But remember, these are in thousand. The values in the p. The 1 means 1,000, 2 means 2,000, 3 means 3,000, and so on. Okay, answer the following question. So for part A is, if the initial population is 3,000, that is means P of 0 is equal to 3. Now this, if looking at this, we can, if we put it here with the differential equation, then this becomes the initial condition. So initially, if the population was 3,000, what can you say about the limiting population? So what is the limiting population? The population at time t is greater than, and t goes to infinity, plus infinity. So after a very large time has passed, and a lot of time has passed, what will be the population in the community? If you notice here again, look at the flow of the direction field or flow of the solution there. So it looks like going something like this and becoming like a horizontal or a constant as t goes to infinity. But what is that constant? That is 2. So this is a line y is equal to 2. So this is becoming like an asymptote to the solutions. If we are coming from above, also it is becoming level to the p is equal to 2 value. So the limiting population will be 2. So limiting population is, well, the value is 2, but the population will be 2,000. So that will be the limiting population. Why? Because from the direction field we see that P at t is equal to 2. As t goes to infinity, P is equal to 2. So at 2, all the curves are joining at 2. So it means no matter where the population starts, whether below 2 or above 2, it is going to level off at 2. Means at a level of at 2,000. The next question, and also note one more thing. if you look at the given equation or given differential equation, what is happening? If you dp by dt, or your rate, if you set it equal to 0, this means p times p2 minus p is equal to 0. So this is going to give p is equal to 0 or p is equal to 2. So this is what we are looking for. So where the rate is becoming 0, no change in the population. So when does that happen? When the population is 2, or down here when the population is 0. So if there is no population, there can't be any rate, so rate is 0. But when we have population and it lies, it can be anywhere between 0 and a higher number, and then it will level off at, eventually it will level off at 2000. So can a population of 1000 ever decline to 500? What does that mean? It means if we start at a 500 like here, can it go like this? Can it become level off with 0? Well, you can see from the graphs, or from this direction field, you cannot see a graph like that. You cannot see a curve going in this direction in the direction field. So that means no, this cannot happen, because even if it is started at 500, it's going to go level off at 2000. So no population, because the limiting population is 2000. So a population of 500 will eventually, we can say, level off at 2000, or eventually grow to after it grows to 2000, it doesn't go above 2000, because that's why the line p is equal to 2 will not be crossed. So it will just level off at 2000. Then next example question is, can a population of 1000 ever increase to 2000, to 3000? So it means it's saying that if the population started at 1000, so will it go to 3000, which means will it cross this barrier and go to 3000, level off at 3000? No, that's not going to happen, because it will not cross the threshold of 2000. The limiting population is 2000. That threshold cannot be crossed. Okay, now from my side I'm adding another question. What if the population starts at 3000? Will it grow to 4000? Again, answer will be no. Okay, so will a population of 3000 become 0 or become 1000? Well, there is almost no chance, because a population of 3000 will again level off with the 2000. It will come down. It will not grow. It will come down and level off at 2000. Okay, next example is actually from the exercise. So it says a model for the velocity v at time t of a certain object falling under the influence of gravity in a viscous medium is given by this equation. That dv by dt means rate of change of the velocity is equal to 1 minus v over 8. From the direction field shown below, so this is the direction field, and its first part is saying sketch the solutions with the initial conditions v of 0 is equal to 5, 8 and 15. So we have three initial conditions. One is v of 0 is equal to 5, another is v of 0 is equal to 8, and another one is v of 0 is equal to 15. So we get three. We have to draw three different curves, solution curves. So v of 0 is equal to 5, so it means 0, 5. So this is, by the way, 2. This is 2 here. This is 4, 6, 8. So you see it's leveling off at 8 because we are seeing this horizontal line. So if you notice what is happening, again similar to what we just saw before. So anything here, it's going to go increase, not like a straight line, but it's going to go like this and level off at 8. And anything from coming from up, we level off at. So we have to draw the ones for the 5, 8 and so this one is almost like the one with the 5. So this one will be v of 0 is equal to 5. So what about 8? So 8 is over here, so the 8 one will be just the horizontal line. What about 15? Well, okay, 10, 12, 14, 16. So v will be something here. So we are coming like this, and it's again going to level off at 8. It will take a little bit longer to get there because of the slow moving, changing these constant lines, tangent lines, but eventually it's going to go to 8. So this will be v of 0 is equal to 15. Then it asks, why is v is equal to 8 called a terminal velocity? Okay, so we call it a terminal velocity. The v is equal to 8. And why is it terminal velocity? Because all the curves or all the solution curves are leveling off at v is equal to 8. This is the t curve, by the way, t line, and this line is representing v. Okay, so all the curves are leveling off, so it is called terminal velocity. So v is equal to 8 is terminal velocity. Because that is the limiting value of v, like in the previous example we saw. Because v is equal to 8 is the limiting value of the v from the direction field. Okay, what does that mean? Because that means that limit of v as t goes to infinity is equal to 8. That's why we call it a limiting velocity. Okay, another example from the exercise, problem number 6. So it says, consider the differential equation dy by dx is equal to x plus sine of y. Now this one, I cannot show you the solution yet, like the ones I showed you in the previous video. Neither for that one. Well, this one we could, but for now just leave it as it is. So we will learn the solutions in next chapters. But this one we can talk about now. We are not even given the direction field, but probably we can give answers without the direction field. So the first part is asking, a solution curve passes through the point 1 pi over 2. What is the slope at this point? Well, slope is the value of the dy by dx. So slope will be equal to dy by dx at the point 1 pi 2, which means wherever I have x, I replace it by 1. Wherever I have y, I replace it by pi over 2. So it will be 1 plus, so sine of pi over 2 is 1, so I get 1, so it's equal to 2. So the slope at this point will be 2. Then B part is saying, argue that every solution curve is increasing for x greater than 1. So it means when x is greater than 1, the solution curve, no matter which solution curve we are looking at, it will be an increasing function. Which means for x less than 1, we are not sure. It could be decreasing, it could be constant, it could be increasing, but definitely for x greater than 1, they will be increasing. So how do we tackle that, or how do we look at that solution or answer for this question? Well, how do you know a function is increasing? If the function is given, maybe we can graph it and see that it is increasing, but the function is not given, but we are given the rate of change of the function. So if you again recall, a function will be increasing if its first derivative is positive. So what we want to do is we want to see where is the dy by dx going to be positive. So we want dy by dx greater than 0. So that then our yb will be increasing. But note here that now we know that -1 is less than or equal to sine of x, which is less than or equal to 1. So the sine x lies between these two quantities, and x is greater than 1. So when x is, because that is the condition we are looking for. So when we have this situation, so what can you say about x plus sine x? So x is greater than 1, right? So x plus sine x. So you can see this will be bigger than 0 and will be less than well, it will be greater than 0, right? We don't care about how much is this, because this will be not less than 2. It will, between 0 and 2. Okay, so the value of x plus sine x will be between 0 and 2, which means it will be positive. And that's what we had to show, that the function will be, the value of the function will be positive. So x plus sine x is positive, which means our function is increasing. Because if this is positive, it means dy by dx is greater than 0, which implies the curve is increasing. Then the question says, show that the second derivative of every solution satisfies this equation. So basically we have to find the second derivative. So first derivative, remember, is dy by dx is equal to x plus sine x. This is what is given. So I will now differentiate this again. So we get d2y by dx2 is equal to d by dx of, sorry, this was sine y. So x plus sine y. Now this is a sum, so the derivative can be distributed. So it becomes d by dx of x plus d by dx of sine y. Now this first one, because we are differentiating an x, term involving just x with respect to x, so the derivative is just 1, plus, now we have a y in here, so we are differentiating a function of y with respect to x. So the answer will be, remember, it will be like the implicit differentiation. It will be cosine of y times dy by dx. Okay. Now remember that dy by dx is only with cosine, not with 1. Okay, but now we can simplify this further. I could say 1 plus cosine of y, because we already know what is dy by dx, what is the value of dy by dx. So we replace the dy by dx by that quantity and then just distribute. So we get 1 plus x, was it 2y? Well, this is my mistake, sorry. I think I got this one. Oh, okay, just leave it like that. No mistake there, my bad. So x times it's 1 plus x cosine of y plus cosine of y times sine of y. So this is what we get. But this is not the same as that, but you can see we can make it do like that by doing what? So I'm going to divide it by 2. So 1/2 times 2 cosine y times sine y. But what is this? This is sine 2y. So just rewriting it in that form. So we get the required So this is the required result. Okay. The next one is saying a solution curve passes through 0, 0. Prove that this curve has a relative minimum at 0, 0. Okay, let's see. How do we find that? Does anyone remember that? So we can use because we already know the second derivative here. So we are going to use the second derivative test. Now how do we do that, if you recall? So second derivative test. Now we already know that dy by dx at 0, 0 is going to be 0 plus sine of 0, which means 0 plus 0, which means 0. So the dy by dx is 0. What does that mean? It means 0 is a critical number. What about d2y by dx2 at 0, 0? So at 0, 0, the d2y by dx2 will be 1 plus 0 into cosine of 0 plus 1/2 sine of 0. Now sine of 0 is 0, cosine of 0 is 1. So we are getting 1 plus 0 into 1 plus 0. But this is a 0 again, so we end up getting a 1, which is greater than 0. So by second derivative test, now if you recall, so we have relative min at 0, 0. And why is that? Because the second derivative at 0, 0 is greater than 0. So this is the second derivative test, which says that if at a critical point the second derivative is greater than 0, means the second derivative is positive, it means we have a relative min value at that point. If the if the second derivative is negative, then we have a relative max at that point. So this is how, without looking at the solution, we can answer so many questions about the solution. So this is section 1.3, and now we are going to jump on to next chapter 2. So in the next video, chapter 2. Okay, see you.